Welcome back to Beyond the Patterns. It's my great pleasure to introduce today's speaker, Professor Xiaolin Huang, whose exceptional career and groundbreaking research makes him a true leader in the field of machine learning and optimization. Professor Huang began his academic journey at Jiao University, where he earned his bachelor's degrees in 2006, followed by his PhD at the prestigious Tsinghua University in Beijing. His passion for advancing the frontiers of knowledge took him to East Stadius, KU Leuven, where he excelled as a postdoctoral researcher. Soon after, he was honored with an Alexander von Humboldt Fellowship, which brought him to our very own pattern recognition lab at Friedrich Alexander University, Erlangen-Nuremberg. In 2016, Professor Huang joined Shanghai Jiao University, a role that has only grown in prominence, culminating in his appointment as full professor in 2023. Today, he serves as the Vice Dean of the Department of Automation, guiding the next generation of scholars and engineers. Professor Huang's research encompasses a diverse range of topics with a primary focus on generalization in machine learning, bridging the theoretical insights with a practical application approach. His works have appeared in top-tier venues such as JMLR, IEEE Transactions on Pattern Analysis and Machine Intelligence, NeurIPS, ICLR, CVPR, and IEEE Transactions on Medical Imaging. Notably, his surveys on piecewise linear neural networks in Nature Reviews Methods Primers underscores his ability to distill complex concepts into profound insights. Beyond his scholarship, Professor Huang contributes actively to the community, serving as an editor for machine learning and as area chairs for leading conferences such as ICLR, CVPR, and ICCV. Today, Professor Huang will guide us through a fascinating exploration of generalization in machine learning and the emerging concept of machine unlearning, a critical topic in the age of AI, ethics, privacy, and trust. Dear Xiaolin, the stage is yours.
Okay, thanks a lot for the introduction. And actually, I always say that I like the time I spent in Erlangen, and I always want to have a chance to go back. But before I going back physically, now I go back, online to have this talk. So I'm very glad to have this opportunity to introduce some recent idea on machine learning and machine unlearning. So maybe it's not very, actually, very starting point for understanding something. So I hope that we can together to think about something, and maybe this is the main purpose of this talk, and we can have a lot of opportunity to discuss that. So the machine learning and unlearning, the view of generalization, I will talk about actually 4 parts. First is why we actually rethink the generalization capability for deep learning. There are a lot of interesting and actually some puzzles we cannot understand very well. And from that puzzles, we propose some new idea. First is the dynamic low dimensionality for learning, and also for unlearning. We have some works and then conclusion. So I think we have now very powerful machine learning methods. However, think about the basic idea. that the way we communicate with the computer, with AI, is as the same as the previous times, that we are still doing something like first sample some data from unknown distribution, and then we establish a function to run a function to fit the training data, and then use the data for new things. The things is the same, but what changes in the past time from shallow model to deep model is that the models becomes very flexible. We have huge number of parameters, so we can easily achieve zero error. That is, for training data, we can always get very accurate result. However, this is not what we really want. We really want is that to have a model which is very good on test time, on test data. So we want to have test error very small. So there is some gap. This gap is generation capability. We want to minimize the gap between training and the test. The practical machine learning tells us if we use deep models that we can have very good results. That means we can have very good performance on test data, have very good generation capability. But how to understand this? If we think or we ask ourselves, when we train neural networks, can we trust the result or not? We think that we have two situations that we can believe that we get a very good result. The first is that we have sufficient data. It seems that this is the case for deep learning because deep learning always have a lot of data. However, compared to the number of parameters, we cannot say we have sufficient data. The number of data are always not sufficient. For example, this starting task that everyone here are very familiar with is the CIFAR-10. It has 50,000 images. However, we use this kind of images to train millions of parameters. For example, in VGG, we have 28 million parameters. That means if we compare the ratio, that means we use only 5 data to train 2,000 parameters. So we cannot say that we have sufficient data. Actually, the number of the data is too small. However, we get a very good result. So this is not the reason. So we should to find another way to explain. So we think maybe the data is very dense. That means although we have, for example, we have 50,000 images, and any new images is just nearby the training data, then we can say, okay, we can trust it. We do not worry about the generation capability. However, this is also not the case for CIFAR, because for CIFAR, this is a 32 by 32 colorful images. So the dimension is about 3,000. We only have 50,000 images. They are very, very sparse in a space with 3,000 dimension. So the question comes that on the one hand, we do not have sufficient data. On the other hand, the data are very sparse. Why the performance is quite good? Why we can guarantee a very good generation for deep learning? This is the problem, and a lot of discussion on that. For us, we propose a hypothesis that the training dynamics is not in a very high dimension. Maybe it's in a low dimensional space. What does it mean? First, the degree of freedom in training is the true complexity. It's not the number of parameters. For example, we have a model with millions of parameters. However, only one parameters can be tuned. Then the complexity, the freedom is only one, not 1 million. This idea also can be generalized, that to be not only one parameters, but we have very strong link among parameters. For example, we have one freedom that all the parameters should be added together, should be decreased together. Then what we can tune is only the magnitude of the change. Then the complexity or the degree of freedom is only 1. This is the case for deep learning. We think the training dynamics in deep learning is in a low dimensional space. That does not mean that only a few parameters is meaningful. That means the parameters are coupled together and changed together. So the true degree of freedom is very small. For example, here we have 3 parameters to tune, and then the trajectory is W0, W1 to W3. However, if we can find a subspace like the blue ones cover the trajectory, then the true degree of freedom is 2, not 3. Why? Because we can train this on the plane on a 2-dimensional space and achieve almost the same result. Then we can claim that the degree of this system is 2, not 3. But we can say that, and someone can do not agree with that. So how to verify the hypothesis? I think the golden standard is that can we train the neural networks in such low dimensional space to achieve the similar result? If I indeed can train this system in this by the 2-dimensional space to achieve almost the same result, I think everyone can agree with me that the system has 2 degree of freedom, not 3. Okay, so this idea is partially supported by the previous experiments. Like Google DeepMind, they try to train neural networks with only 9,000 dimensions and achieve about 84% accuracy, or 556 dimensions to achieve 70% of accuracy. The accuracy here is not very high for a CIFAR task. However, it's promising. It means that we can indeed achieve some meaningful result, although not very good, but meaningful. And we found that how to construct this subspace, the idea is to cover the dynamic trajectory. If we can cover the dynamic trajectory, then we can find a very good, very small subspace, and on that subspace we can achieve similar performance as training all the parameters. So we tried for different models. You can see we tried different models with different number of parameters, but we can construct a 40-dimensional subspace and train on this 40-dimension subspace to achieve almost the same result as training all the parameters. I think this can verify that indeed the training dynamics is in a low-dimensional space. And this is a paper last year we published in PARMI. And following this idea, the very nature that we think it can be used to speed up the training, because we change the problem of optimizing millions of parameters to minimizing only 40 variables. So it seems that we can speed up. So we set up a project with Huawei, and we say that we can speed up your training. However, when we really use this method in industry, we found the problem. We indeed can find a low-dimensional variable u, the dimension, for example, only 40, instead of w, the original parameters, millions. However, we need to project it. So we have a projection matrix. The dimension is d, the 40, n million, d times by million. When we apply them into the real neural networks, industrial neural networks, we found that it's terrible because n becomes to billion. So there's no GPU who can even store the projection matrix. So we meet a big problem. And we found that fortunately we can start from the PCA to find a very good representer theory, saying that the result of PCA actually in the span of the training data, or that is the result is actually the weighted sum of the training data. This is not the training data, but the historical solutions. And then using this idea, using this formulation, we change the projection into a weighted sum, and we can fully utilize the structure of neural networks. We can calculate the combination layer by layer, and a lot of operator is very friendly to the layer by layer structure. Then we can efficiently train or obtain the U to train that. So this is what we call the TWA trainable weight average, because the averaging weights could be trained. And this is a paper in ICLR and ECCV, and we actually can train neural networks, which is actually following a VIT plus BERT structure, has 1 billion parameters, and save the training time by 30%. Of course, there are a lot of engineering problem, that how to do parallelize, how to do quantization, how to do many speed up technical, but finally we achieve this result. So Huawei thinks that this is very good. So they include the dimension reducing training method in their -4. This is their own platform for trainings. In their official codes, we can use the dimension reduction training problem. And after finding that we indeed can find a very low dimensional space to include to cover the training dynamics, we think that why we can use only 40 degree of freedom, 40 variable instead of millions parameters to train. We think that this is closely linked to data. Because of data determines the training trajectory. So the low dimensional structure comes from data. And we can use this one to explain the existence of adversary examples. Think about one sample. Our neural network training, the objective is the summarization of the loss function from all the samples. Each of the samples will propose a requirement saying that your neural network should change in this direction, in the gradient. If the neural network can change in this direction, then the error on this sample could be minimized, could be decreased. However, we have many samples, so for each of the samples, propose a direction. So totally, it can be imagined that we have the dimension of the trajectory should be similar to the number of parameters, maybe millions. However, we said we only have dozens of dimension which can cover the whole training trajectory. So this one is largely smaller than the number of parameters. That means we have a huge space where the direction has not been used. So there exists some sample which is similar to the original sample in the image level. However, the direction it requires could be orthogonal to the training samples. They are adversary samples. Adversary samples have been investigated for several years. That is, we can construct some, actually this is the nature one, this is the adversary one. They are very similar. However, this is correct, this is incorrect classified. So we do not know why. We can create them, but we do not know why. Now we know why, because this dimension is quite small. So there are a lot of huge space that have adversary samples which can have direction orthogonal to the nature data. And we also think about that to verify this this claim that we can establish another experiments is that if we put the adversary samples to training, what will happen? That is similar that if we put the adversary samples in training set, we train the adversary samples, it does not help any nature samples. For example, this is the samples we created. This is reported in last year actually, that we put permutation only 2 over 256, so the permutation is very, very small that people cannot see it very clearly. And we can provide these images to neural networks, and neural networks indeed can train. We can train a very good neural networks. The training error is very small. However, there is no generalization capability. That is, cannot predict the nature samples. So this can be explained in the same way. We put this into training data. Of course, it does not help any samples which have direction orthogonal to the training data. And this also can be used for OOD detection because the subspace is close linked to training data. By training, the neural networks finally can be adaptive to the data of the training data. That also means that the neural networks is not adaptive to other data, for example, out of distribution data, OOD data. So we think the gradients, the subspace of the gradients can help us to identify the data is ID or OOD. Previously, for OOD detection is that people use forward features, and based on that they can establish neural networks or you do KNN to identify the OOD. And now we think that we can use the gradient to extract the subspace to identify ID or OOD. However, this idea is quite nature, right? Just followed our previous discussion. However, we will meet a problem, technical problem, because the dimension of the gradients is equal to the number of parameters. That will be millions or even billions. It is terrible or it is impractical to deal with that. So we also propose to use some class-wise average or other technical to efficiently calculate to capture the gradients information, and then we can use them together with many OOD detectors and to achieve very good actually the SOTA performance on many data sets. So we recently have two papers, one in TPARMI, one in IGSV, to use this idea to find a good to well classify ID and OOD. Okay, so this is in the view of training, we found that finally we can find a subspace to, actually this is a gradient subspace to describe the data. And we also can use this idea. This idea comes from generalization capability. And we also can think about the generalization capability in the view of machine unlearning. So we always ask us a question that why the deep neural networks has very good performance, very good generation performance. Is that the case? DNA really remember something? I think now the question for this answer for this question becomes more and more clear that indeed the DNA can remember something. For example, in GPT, we can design some prompt to let the GPT tell us some private information like the address or the fax number. And this is the case that the ChatGPT tell us the private information without accessing the training data, without accessing the internet. So this one is actually remembered in the parameters. We can also have this very direct verification is a task called the training data reconstruction. First, let's think about the training process. For training process, it actually can be viewed as a mapping. This mapping is that when the algorithm is given, for example, we fix some randomness like the seed, like the batch selection, like the learning rate. We all fix them, so the algorithm is fixed. If the algorithm is fixed, the results, actually the parameter of the model, is determined only by data. We have this kind of data, we have this kind of parameters. We have another set of data, we will have another model, another kind of parameters. So this is a mapping. This is training process. If we think that the training process really remembers something, we can actually do another thing. That is, can we reconstruct the training data from W? If W remember all the data, then we can solve this inverse problem to extract or reconstruct data, training data from W. If this is a mapping, this is another mapping, but very complicated. So a direct verification for memorization is that can we reconstruct it? There is a very interesting and pioneer works I want to introduce is that for CIFA image that this is a training data set. Then we use CIFA to train, they use training data to train MLP. And then they have parameters. And then they solve a inverse problem, something like this one. And finally, they can reconstruct data similar to the previous one. This is they didn't touch again the training data, but from the parameters they can find this one. However, there's a limitation that they can only deal with this on MLP. For MLP, especially very broad MLP, the training dynamics is very linear. Then that means we can using the initial parameters and the final parameters to estimate the gradients. And when we have gradients, we can reconstruct the data. So we think that can we extend this idea into nonlinear dynamics, that is some practical neural networks, not MLP. And this is our recent work. We submit to ICLR and the score looks good, but I do not know the final result. Hopefully we can publish it in ICLR next year. And we use ResNet. ResNet is the dynamics is quite complicated. That's actually very practical, and we train CIFA, and the second and the fourth row are the original data, and the first and the third are the one we reconstructed from the trained parameters. You can see it is similar. It is not exactly the same. So the SSM, the similarity is the number is not very good, right? However, the semantic meaning can be recovered. It lacks the human being's memory. For some old friend that I can roughly think about this appearance not very accurately, something like that, right? We can also use it to in VIT structure in ImageNet. This one is the training data. This one is what we reconstructed from parameters. We can also use them in an NLP task. This is the original sentences, and this is the initial guess. They are meaningless, right? However, when we minimize them, we optimize them, we can finally have the reconstructed one. So you can see this is the same, and for some, this is not very accurate. However, I think the semantic meaning has been reconstructed. So we think that indeed, after training the neural networks, it remember something. If we agree that the neural networks remember something, we have a very crucial problem that memory erase. That is machine unlearning, because we always have the right to be forgotten. Maybe it comes from the privacy or becomes some harmful information be found that we need to remove them. For example, we have Twitter. account for ourselves. However, someday maybe I dislike it, or maybe I have something new, more interesting. I want to deregister. I want to quit Twitter. Before that, simply I quit. I delete. I delete all the information there. Then I think it's no problem. However, if the Twitter has used our data to train a large language model, then our information has been remembered by such large language model. So simply remove some information from the data set does not work. I require them to forget me. I require them to retrain the networks. However, this is impossible, right? So we have the problem that machine learning, the key word is effectively. When we have training data and algorithm, will have the mapping, we map the training data into parameters. If I quit, I ask the Twitter to retrain their neural networks. They should have neural networks with training without my own private data. However, this is impossible or is very costly for the company to retrain. So they want whether we can starting from the original one and I remove one data out to effectively go to this one. This is the machine learning, effectively remove the effect of the forgetting data. How to do that? For machine learning, it is quite easy that we give data to the neural networks it's learning. But we want to unlearn. We want to forget something. This is very difficult. The current method follows, generally speaking, they follow the behavior. So the basic idea, one method is called bad teacher. I like this name. The bad teacher is actually a very good name to identify or to illustrate what the machine learning doing. For the forgetting data, they change the Y into incorrect labels. So this is a bad teacher. When I want to forget cat, then I tell the neural networks, this is a cat, this is not a cat, this is a dog, this is a frog, this is a duck, this is not a cat. So I give incorrect labels to do machine learning. However, the key point is that this incorrect information will let the neural network forget something, but also have very bad effect on the correct information. So the key point is that how to keep the correct information which has been learned. For example, I want to forget the nude chef. When I forget nude, maybe I get a non-nude chef, but it's not a chef. I put clothes on them, however, it's not a chef. So the key point is how to keep this. We propose that we can add some Hessian metrics, that is, we use the remaining data to contract the counter map. We use the counter map to adjust the direction, not only to follow the incorrect labels, but also to keep the original Hessian direction for the other information. Then we can get a non-nude chef. This also can be used for generative model. For this kind of things, for the pre-trained model that we have a lot of animals. Here I want the model lose the capability of generating dogs. So if we retrain it without any dog images, then we have a model can generate other animals very well, however, cannot generate dogs. But we use the existing method, you will see sometimes it can indeed ruin or destroy the capability of generating dogs. However, they also meanwhile destroys the other classes. And if we use this method, it can be much better that we can forget dogs, meanwhile keep the other images quite well. But although we have some modification, I do not like the idea of bad teacher. I think this is not the correct way to do machine learning. We should not try to rely on incorrect information. We should rely on correct information. If we use incorrect information, we always injecting incorrect information, which can actually destroy or at least make the neural networks worse. So this will have a problem over forgetting. We propose that it's similar like the example I raised before. When I want to forget the cat, I tell the neural network, this is not a cat, this is a dog, this is a duck, this is a frog, this is kind of incorrect information there. Maybe sometimes the neural networks remember even deeply for this kind of things because he know why this is not a cat. I think this is a cat. You tell me this is a dog. I should remember that. So maybe over forgetting means that it remember this kind of things even worse than before. So the current machine learning method like the bad teacher, they relies on very careful parameter tuning. If the tuning is not very good, they will have very bad performance like here. So how to keep, how to avoid over forgetting? I think essentially we should not rely on the bad teacher idea, not rely on behavior. We need to find something more essential to distinguish training data and test data. A cat is in training data, it is a cat. A cat is in test data, it is also a cat. We should not call it a dog, right? So what is the essential difference? I think this should be generalization. Training data are the parameters, the generalization, the prediction on test data, while the test data are generalized by the training data. If a cat is in a training data, that means I know this is a cat, so I can predict other cats as cats. If a cat is not in the training set but on the test set, what does that mean? That means I remembered, I understand the training cats. Now I can predict this cat is a cat. So the direction is different. The generation direction is different. So following this way, we propose that we should not simply change the labels. We should change the effect on the generation. But this is a technical, very hard. So we only make a very small step. That is, we use the input sensitivity. That is the influence of the input data on the final result. Use this one to to distinguish training data and the test data. And we want to unlearning that we make it small because in training data it should not. In training data, it indeed have very large influence on the final output. However, for test data, it should not. Okay, but this is actually have some radio term. We in our paper we claim that this is very not in numerical experiments we can find that this is small. However, in theoretical discussion we cannot show why this is small, but practical thing that we think it is small, and then we minimize the input sensitivity, we can achieve very good unlearning performance. This is our result. You will see that this is the remaining accuracy, this is the forgetting accuracy, this is the test accuracy, this is the retrain. So this is the standard. This is the golden standard, that is the retrain model. We all the method want to be as similar as the retrain model. However, you will see that the performance of our method is similar to the previous ones. However, this is the first remaining data-free method. That means for the other method, they all use remaining data, but we think that this is not a good thing. when we do machine learning, we have millions of training data, and we want to forget two, for example. We want to effectively forget the two, so we should only use this two. We should not, again, use the millions of data together. That is, we should not use the remaining the millions of data. We should only focus on the 2 points, two samples we want to minimize. We want to forget. Okay, so this is the first method that achieve SOTA on learning performance without using the remaining data. We hope that this is what we submitted to department. I wish that we can get appreciate from the reviewers. Okay, so this is just some, you will see that this is just some draft, but I want to share with the colleagues in our lab, in our pattern recognition lab, in FRU, and look forward to some discussions. So the first thing is that we think generalization is very important. For classical models, we have very beautiful theory. However, for deep models, there is no very convincing theory, although the performance is very good. So I think we need to think about generalization in different ways. And today's idea from low-dimensional dynamic space is only one new point of view, and I hope this can bring some new idea. Think about it in this way. So generally speaking, in technical part is that we propose a method to cover the whole trajectory, and then we can use this subspace to do a lot of things. For example, fast training, for example, adversary, the ones unlearnable samples can explain by this way also for OD. This is the fourth generation improvement. We can also break generation. That is to do machine learning. But of course, for our method, it's only a very first step for break generation. If we can find more, I hope and I believe that there are many methods which can deal with generation to break generation that can have much better performance than ours in machine learning tasks. And finally, I acknowledge my students. And the blue ones is for theory. These guys are for optimization, and these ones are for machine learning. And as I said, I discussed with Andres that maybe next semester we can establish uh, some joint program, and then I hope that the people in FRU and people in Shanghai Jiao University can communicate more and to do some interesting works. Okay, that's all. Thank you.
Absolutely. Thank you for this wonderful presentation. It was very, very insightful, and I enjoyed it very much. And I have a short round of applause for you. I'm just not sure whether it will be broadcasted properly. I have knocking on the table pre-recorded, but it might be filtered out by the Zoom noise filters. Could you hear that?
Yeah, no problem. Yeah.
I think it was filtered. Okay, so Xiaolin, thank you. This was really a brilliant presentation and very much in our interest. And there's many questions in the chat, and I'll just go through them step by step. And I think it will start with the beginning of your presentation. And
Yeah.
I think this is more like an observation that is very much with your works with the intrinsically rather low dimension. So we now see also a lot of works in published that rely on like foundation models rather as feature extractors to use them for dimensionality reduction in order to extract embeddings and then train only on the samples in the embedding. And I think this seems to be very in line with your considerations. Can you comment on that? Do you think it's a good idea to use foundation models to extract embeddings and then work in the low dimensional spaces?
Yes. I totally agree with you that I think why the training dynamics is in a low dimensional space because the data is in a low dimensional space, and here that we didn't rely on embedding, so it relies on the natural low dimensionality of the data. if we can use the foundation model or other model to extract a low dimensional space, then I think the information is more dense, or we can say the dimensionality is even smaller than the natural ones.
Mhm.
So I think if we can rely on the embeddings, I think the dimension of the dynamical dimension maybe even smaller than the nature data. Yeah.
Yeah, I think it is the case because you show in your results that you have like 40 some dimensional sufficient. And if you
Mm-hmm.
think Cypher 100 is a 100 class problem, right?
Yes.
Then it should have like 99 dimensions if it were like linearly separable, right? But you can
Yes.
go out down to 40, so there must be even lower subspaces. Do you have any idea on the structure of the subspace or why this emerges?
Yeah, it's quite good question. Actually, I want to know, but very, very hard. I think it's very meaningful because we know, for example, it's 40 dimension. That means the parameters are coupled together when training. So if we can really understand the structure, then maybe we can also reduce the forward structure. Nowadays, using our method cannot reduce the forward because we actually find the link in training, not the link to the forward. So that is because we haven't understand very well for the link between different layers or different parameters. If we can find something, we can find a very small neural networks because
Mhm.
it is very strange that, for example, we only 40 variables we can train a neural network. However, in the forward, we still rely on millions of parameters.
Right.
It is somehow strange. This gap is too big. So maybe one day we can find that. But this is, as you said, maybe the first step is to understand how
Yeah.
they are linked together. Yeah,
There must be some more redundancy, but
how
it
to
would be
find them?
interesting to uncover it. Yeah.
Yes, yes,
Um,
yes.
your results on adversarial examples, I found that striking. But this is more a property on the distribution of the gradient spaces than on the dimensionality reduction itself, right? Because
Yes.
if you had the perfect like linear dimensionality reduction, it should map adversarial examples into the null space of the projection, right?
Hmm. Yes, yes.
So
Uh,
that would be my understanding of a feature extractor, right?
Yeah, this is not, this is, I think this is different to the feature extracting or the feature dimensional. And they are linked together, of course, but not determined by each other. Because the features means that we, how to say, because the features affect the gradients via the neural network structure. So the forward structure and the backward the structure is totally different. So they are linked together, but it's very hard to, for example, when we have a very good structure or understand from the feature embedding and to obtain the backward structure, or else if we already have a very good projection here, projection matrix to understand the for backward information. However, this cannot be directly used to extract feature low dimensional space.
Yeah, but,
So
but it's interesting to think about that. If I mean, technically, there should be a dimensionality reduction method that neglects or ignores the adversarial attacks and maps them
mm-hmm,
to a null space. But due to the nature of the gradient update and the weight directions,
mm-hmm,
you essentially open this up, right? And it
mm-hmm,
gives you a tool where to expect the adversarial examples.
mm-hmm, mm-hmm. Yeah, for this one, we but here this is somehow explanation to saying that. However, the how to say in training process, the even for this one, even for the natural one, in different epochs, this is changed. So because the final training trajectory, the training dynamics is non-linear. So actually they changes. So although we give explanation here, but still we very hard to use this idea to, for example, as you said, to detect or to remove the adversary to enhance the robustness. Still, I didn't find a very technically sound way to deal with this one.
Right, right, correct. Yeah. I mean, in a linear world, everything would be easier.
Yes, yes, yes. When people can understand the linear very well,
Yes.
non-linear.
Right. The reconstruction of your training data, I think that is very impressive work, in particular for the Resonate 50. That's something that is super interesting. Um, can you comment a little bit on regularizations that you have been using to reconstruct the training samples, in particular for the images and for the text? What kind of regularizers you added for the inversion process?
Yeah, it's quite good. Actually quite insightful. We tried a lot of regulation term, however, found that the regulation term does not help a lot.
Okay,
For example, it's quite nature that we think about the total variation
right.
to to improve the performance. However, it's not very useful. It is useful. It can increase, for example, you make this is smooth, for example, but
Mm,
not very useful. So we simply this is called a simul die. That is, we want the training trajectory of the training and the reconstructed one have similar dynamics. As then the supervision information maybe is very strong enough, so the regulation does not help
I
very
see.
well.
I see.
Mhm.
But then you essentially need information on how the on how the weights were updated, right? So you need a history of the training process.
No. We only need the initial and the final.
I
But
see.
we tried that, for example, but indeed, if we know how many steps, we know how large the batch size, we know the learning rate, then it is helpful. But even we do not know this kind of information, still we can extract, maybe not very good, but we can extract some meaningful result from the parameters.
Impressive. Very, very impressive.
And
Um,
also for me,
yeah,
I like this work, although this has not been accepted, but I like it. I like this one. Yeah.
yeah. It's very impressive, and I think I think these works are also very important for people working in the medical domain because they want, people now think if they publish models that they are anonymous, right? And but you might be able to attack them and reconstruct training data, patient health data, and so on. And to be honest, that is also probably a kind of weak point for many of the federated learning approaches because they
Yeah.
exchange model parameters and then you could extract training data from that as well. So this is a very important work for the medical domain, I think. Also, all the work on unlearning and forgetting is of course very important for the medical domain.
Mhm.
And I just see here exactly when you say X forget. So how important is it that X forget is kind of independent of other observations? Because I mean, right now you showed it rather for classes, like for specific types of dogs. But if you have in a medical domain, it's a specific patient, and that patient may be very similar to other patients.
Mhm.
And can you comment on how important it is whether or not the sample can be reconstructed by interpolation from other samples?
Yeah. It's quite important question. That if we want to forget one or two sample, not a class, the problem becomes more difficult. Because if we only forget two or three or specific samples, the difference between the forget and the pre-trained model are not very significant.
Mhm.
So it is very hard. And the more hardly is that, as you said, that if we have data which is quite different to the others, then it is easy because it affects the model very well. Then we can, not very well, very large, then we can find the effect and remove it. If, as you said, that it can be interpreted by the other ones, then it is very hard to unlearn because it's very hard to distinguish whether this is in training or in the test.
Mm,
So it is indeed very hard. Yeah.
mm,
But I think it is also concerned with the topic of this size, maybe generalization. In the embedding part, this can be represented by the others. So if we only look at accuracy, there is no big difference, whether it is in training or not in the training set, because it can be interpreted by the other samples. However, the generation direction is different. It is interpreted by the other samples, means that it is supported by the other samples. If
mm.
it is in the training set, it means that it should support the others, not the others imperated me. That is, I should imperated you. Then maybe the direction can better distinguish them. So I hope that, or I believe that for later machine learning, your task is very good example to evaluate the performance and also to raise the importance why we should consider about it from the generation capability, generation direction.
Well, very, very good. There's many questions in the chat, but I think for the interest of time, I will only ask one more question because, to be honest, there's many, very, many interesting things in your talk, and we should also follow up on this. But let's just ask one more questions here from the chat.
Mhm.
Do you think model generalization can be improved by using adversarial samples in the validation set? So sometimes models at minimal validation loss already heavily suffer from overfitting. So
Yeah.
what do you think about that?
Uh, I think vanillally use the adversary samples. For example, we directly use the sample to train does not help generation because they are in different distribution. All the nature samples are here. If we train here, then we have some harmful effect on the final neural networks. So this is actually this is one very important problem for adversary training society. There are a lot of adversary training methods, and actually the robustness could be improved. However, I actually have done some work before, 2 or 3 years before I do a lot of adversary attack and defense works there. But nowadays I suddenly found that there is no company wants to use the adversary training because although the robustness could be improved, however, always it can decrease the accuracy on nature data.
Hmm.
I think basically the distribution of the adversary samples and the nature samples are different, so maybe it cannot help a lot. That means vanilla use that. If we can find some good way to use that, maybe. But nowadays, I think for all the adversary training method, does not help the generation capability.
And it opens the path for new adversarial examples, right? That
Yes.
you can always come up with yet another attack.
Yes,
Yeah.
yes.
Yeah. Xiaolin, this presentation was wonderful, very insightful. I enjoyed it a lot. And we also had a very vivid discussion afterwards, many questions in the chat. And I thank you very much for the presentation and being here with us. And
Thank you.
yeah, let's give you another round of applause.
Yeah. And also
And now I'll stop the recording.